Welcome again. So, we are discussing about the dynamics of the moving system, that means the pointer, the coil, the frame, all these things which move together in an measuring instrument like an ammeter or galvanometer. So, in our last class we have written the equation for the dynamics where we had this J d2 theta dt2. This is nothing but the like the inertia times the angular acceleration plus we had the term k damping constant. Okay. So, let me use a simpler notation for ease of writing. Okay, let me just write it as A, the next term as B, d theta dt. Okay. So, where A is actually J, moment of inertia. Okay. And then B is damping constant. Then plus let us write C times theta. So, where C is basically the spring constant. Okay. So, this is equal to K according to our previous notation. Okay. So, this is spring constant and this is equal to Td, that is deflecting torque. And if we take a particular example of PMMC instrument, this is equal to Gi. So, Gi is equal to Td deflecting torque for say PMMC instrument. So, let us take the example of the PMMC instrument. We can consider any other instrument, we will have similar modifications. Say for example, if we take moving iron or electrodynamic instrument, we have to make this I square and similar modifications can be done, but the basic idea will remain same. Okay. So, the basic idea is that this is the inertia times the angular acceleration. This should be same as the sum of all the three types of forces: damping force, spring torque and the deflecting torque. Okay. And then so let me also write the dimensions of this variable. So, C is like torque per unit angle or angular displacement. So, it may be like say Newton meter per degree or per radian depending on whatever unit you choose. Then these the unit or the dimension of B, damping constant, what will it be? It is again torque, it is some torque per unit angular velocity. So, this will be torque per unit angular velocity, angular velocity. And so, and this is the dimension of this moment of inertia is like, it is like mr square, you know from the physics. So, it's like kilogram, I mean SI unit will be kilogram meter square, something like that. Okay. Okay. So, this is the expression or the dynamics that governs the motion or movement of the moving coil at any instant, at any moment. Now, at steady state, that means we can also say that this is at the equilibrium state where the pointer stops. So, we will have d theta dt is equal to 0, we will have also the acceleration equal to 0 at steady state when the pointer stops at completely at some position, this will also be equal to 0, and then we will have c theta is equal to g I, or theta is equal to g by c I. So, this is nothing but the sensitivity, g by c will be the sensitivity of the instrument. Now, the question that we want to investigate in this video is that how will the pointer move? I mean, will it, if I apply a current, will the pointer reach its final position at once, or will it oscillate and then slowly stop at that position, or then if it reaches that position at once, will it reach quickly or will it go there slowly? So, all these questions we want to find out, and for that basically what we have to do, we have to solve this differential equation. Okay. So, this is a differential equation, second order differential equation, we have to solve this equation. Okay. So, let us assume I is suddenly applied. Okay. So, that means I was say 0 for some time initially, and then it becomes like this. So, this is a step function. Okay. So, this is time, this is current I, and this value of I is applied suddenly. Okay. So, then how will the pointer move? So, how will the pointer move, or in other words, how will theta change with time? So, this is the question we want to find out. Okay. So, maybe that theta will so theta initially should be 0. Okay. So, this is let me draw once again theta here, say theta versus time t. So, theta should be 0 up to this position because there was no current. So, there should be no deflection. So, it should be 0 up to this point of time, and then it will finally reach some value here which is given by this. So, this is theta final. Okay. So, this will be g I by c, but will it reach there at once like this, or will it reach there like this, or will it reach there after some oscillation? So, this is the question that we want to find out. So, for that we have to solve this differential equation, and you can solve this differential equation in many ways. So, I will adapt a simple way here. So, this is the differential equation we want to solve. Okay. So, what I will do, I will for simplicity of solution, I will first call say theta f, which is final value of theta, which we know is given as. So, the final value will be given by the condition when these two terms are 0. So, c theta f will be equal to g I. So, we will have g I by c, this will be the value of theta f, final value of theta. Okay. Okay. Now, I will subtract this theta f from theta. So, let me call the new variable theta prime, which is equal to theta minus theta f. Okay. So, then let us take a derivative. So, we can write d theta prime by dt, this will be equal to d theta by dt. Okay. So, we are redefining a new variable, and then the double derivative of it will be same as this. Okay. And therefore, now let us put this values in this equation. Okay. So, now here we write a d 2 theta prime by dt2, because this and these two terms are same from here, then plus b theta prime by dt plus c, here in place of theta I will write theta is equal to theta prime plus theta f. So, let us write theta prime plus theta f, and gi, we know gi, from this we know gi is equal to theta f times c. So, here we write theta f times c. Okay. So, this will imply this c theta f will cancel from both sides. So, I will have a 0 on the right hand side. So, this is a homogeneous differential equation where I have right side equal to 0. So, this is easier to solve, and we know the solution of this differential equation is given by the solution is given by theta prime, which is a function of t, of course. Okay. So, everywhere here I can write theta as a function of t, theta prime also function of t, but I am not doing it for clarity of writing. I do not want to make it clumsy. Okay. So, here also you can write this is also function of t, this is also function of t. Theta if f is constant, final value of theta is a constant. Okay. So, this will be equal to some constant a times e to the power say alpha 1 t plus b e to the power alpha 2 t, where alpha 1 and alpha 2 are the roots of the characteristic equation. A call it a m square plus b m plus c, okay, equal to 0. So, this characteristic equation of this differential equation, if you solve this, you will get two values of m, okay, or let me use alpha. So, you will get two values of alpha, alpha 1 and alpha 2. So, you put them here, that will be the solution, and where a and b are two arbitrary constants which you can find from the initial condition or the initial value and of theta and the speed, etc. Okay. So, now what will be these values of alpha 1 and alpha 2? Okay. So, this is a quadratic equation. So, you know the two values are minus b plus minus root over b square minus 4ac divided by 2a. This is simple. Now, if B is less than 4 AC, then alpha 1 and alpha 2 will be complex, and they are complex conjugate of each other. Okay, and therefore you can write this solution, you can rearrange this terms of it, and you will find the solution so this will be of the form something like some constant called how do you want to call it, a b c d, let's call d, or okay, let's call it p, okay, times some sine so it will be of this form. Now this theta is not some phase phi. Okay, so you can rearrange the terms and it will be of this form. Okay, and where omega will be this complex part, I mean the imaginary part, okay, and we will also have another term. So this will get multiplied by e to the power some call it sigma t or minus sigma t. Okay, so and this sigma will be this term, this part, okay, the real part, b by 2a. So I'm assuming that you know how to solve this homogeneous second order differential equation, and so you can find the solution of this form, and the value of p and phi, these two can be found from the initial value of theta and derivative of theta. Okay, p and phi can be found from initial conditions. Okay, so if this is so, b is less than 4 AC, we see that the solution is oscillating. It has a sine term, sine omega t, and then the amplitude decays with because of this exponential term. So theta prime okay, so it will look like maybe like this, so on, and the initial value will depend on this phi, which will depend on the initial value of theta prime. Okay, so this is theta prime versus t, and we know that theta is nothing but theta prime plus theta f. Okay, so if theta prime is oscillating, then theta is just theta prime plus some constant, so theta will also be oscillating. So theta prime is oscillating, therefore theta, which is same as theta prime plus theta f, will also be oscillating. Okay, now Now what will happen if I increase the value of B? So if I increase the value of B, keeping A and C unchanged, then at some point B will be equal to B square will be equal to 4AC. Okay. So this term will vanish. Okay. Then B square will become 4AC, and then the solution will not be oscillatory anymore. Okay. So when we, and if we increase B further, then B square will become greater than 4AC, and the two roots will be real. So they will be of the form, of course, minus B plus minus root over B square minus 4AC. Now B square is greater than 4AC, so this will be a positive number. So this will be both the roots will be real. So again, theta prime or theta will not be oscillatory. Okay. So what we see, observe, for low value of theta, low value of B, the solution is oscillatory or theta oscillates, and for higher B, theta does not oscillate. Now B square equal to 4AC, this is the minimum value of B when oscillation stops. Okay. So we call this critically damped condition or critical damping. Okay. So B square equal to 4AC is the condition for critical damping. For B square greater than 4AC, still we will have no oscillation. This we call as over damping. And if B square is less than 4AC, this is under damping, because we will have oscillation. Okay. So as I was saying, if I apply a current suddenly like this, so this is current time, theta can reach the final value after some oscillation. So, this is under damp. So, this is the condition B square less than 4 AC, or under damp condition we can have a situation where theta reaches its final value like this smoothly. This is the condition for B square equal to 4 AC. If we increase B further, it will reach the final value again without any oscillation, but it will now take longer time. Okay, so, this is the condition for B square greater than 4 AC. So, what we want the pointer not to oscillate, because then it is difficult to take reading. We don't want this pointer to settle down quickly, because we want to take readings quickly. So, this is the ideal condition, this is the most desired condition, B square equal to 4 AC, critical damping. If we use over damped condition, then it will take longer time to settle down, which we do not want. And if we use B square less than 4 AC, then it will oscillate, it will also take longer time to settle down. This is also not desired. So, this is the desired, most desired condition. Now, how can we achieve this? How to achieve B square equal to 4 AC? So, note that A and C, so this is the moment of inertia, like kind of the depends on the weight, mass of the moving system. So, this is the spring constant, and B is the damping constant, okay, and B is given by the torque per unit velocity and for say PMMC instrument we have seen this is equal to G square by total resistance of the coil and external circuit if we are considering damping due to eddy current in the coil. Okay, where G is basically BAN whole square. So, let me put the value. And is equal to BA square by former resistance for damping due to eddy current in the former. This one is not controllable because RE depends on the external circuit. So, we should not rely on this term. So, this term we cannot control. This term we can possibly control, and therefore, we should choose a low enough value for R former so that B is high enough and equal to 4 AC. So, we now if we choose, see if we choose low value of R former, or say, let's say we choose first high value of R former resistance. This will imply low B, maybe very low B, and this may imply oscillation or under damped situation. Okay. If we choose, so call this very high. Now if we choose very low, then we will have B very high, implying over damping. That means it will not oscillate, but it will be slow. It will take long time to reach the final position, and we have to wait before we can take the reading. So for some value of R former, so which you can, so what we want, for some value of R former, B square should be equal to 4 AC. So that means B square equal to 4 AC is the desired condition, critical damping, and here we will have, so B, in place of B square we can put the value of this, and now you can choose the value of R former. You can choose it to be equal to BA square divided by root 4 AC. Okay, so this is the desired critical damping. So that's the about critical damping condition. In our next video, we will talk about few more important things regarding the dynamics. For example, we will show mathematically that the moment of inertia should be low, the pointer, the coil should not be heavy, otherwise it will be either oscillating system or a slow system. And we will talk about also few interesting questions regarding this measuring instrument. Okay, thank you.